Hi everyone, I'm Yu Zhe, a third-year PhD student at UC Riverside. Welcome to the talk of our recent work, Parallel K-core Decomposition, Theory and Practice. This is a joint effort with Xiaojun Dong and my advisors, Professor Yan Gu and Professor Yihan Sun. Finding dense subgraphs is a very important task on graphs. There are many methods of defining such a substructure. K-core is one of them. So what is a K-core? Given a graph G, K-core is the remaining subgraph after we remove all the vertices with degree less than K. That means all the vertices in the K-core have degrees larger than or equal to K. For example, for this small graph, the one core is the entire graph since the minimum degree of the top two vertices are 1. And for the 2 core, 3 core, the vertices in the subgraphs have degrees larger than 2 and 3 respectively. The process of finding such 1 core, 2 core until maximum K value is called K-core decomposition. As a subgraph mining problem, K-core can find many applications in social network mining, robustness analysis of infrastructure networks, bioinformatics, and so on. Besides, K-core decomposition serves as a critical component for solving other problems on graphs, including dense subgraph discovery, hierarchical clustering, degeneracy ordering of the vertices, and so on. BZ is a simple and efficient sequential algorithm to solve K-core decomposition. It follows a peeling process. The data structure used to maintain vertices here is an array based on the degree values, which keeps vertices in order using bin sort. We use a 2-core peeling step as an example. The 2 vertices in the first bin will be removed, so we sequentially remove one firstly. And the degree value of the neighbor will be decreased by 1 and will be moved from 3 to 2. Then another vertex removal. Their common neighbor's degree now is reduced to 1. We move it to the first bin, and it will be iteratively removed. We finish the peeling process for 2 core, and this decomposition for degree threshold 2 is called a peeling round. Each step for the removal of the vertices smaller than 2 is called a peeling subround. The time complexity of this algorithm is out of the number of vertices plus number of edges, because each vertex and each edge will be visited once and only once for the removals and the degree reduction operations. So this is the best sequential algorithm. It is simple and efficient, right? You may ask, is it good enough? It is not enough. Nowadays, large graphs may contain billions of edges, especially for large web graphs. In this case, the sequential K-core decomposition algorithm may need a very long time to compute, and we definitely need a better approach to solve the problem. Luckily, nowadays, almost every computer is multi-core. For the K-core decomposition, we consider designing efficient parallel algorithms to solve it. Here are some primitives for parallel algorithms. In this work, we use the binary fork join model in the shared memory multi-core setting. The computation operations can be seen as a DAG with dependency orders. The work of a parallel algorithm is the total number of nodes in this DAG. We call a parallel algorithm is work efficient if the parallel algorithm's work matches the work of the best sequential algorithm. Work efficiency is essential for the design of a parallel algorithm. So why is it hard to get a parallel solution? The straightforward sequential solution utilizes a bin sort-based array, which is not open to any parallel operations at all. If we take a closer look at the parallel process, we can describe the difficulties into 2 dimensions. First, how can we gather all the vertices with 13 degrees, which are the vertices to be processed in the next round? For the sequential algorithm, we can keep them into a bin sort-based array, but it can be parallelized. The second challenge is to efficiently peel or remove all the vertices we just gathered. We want them to be removed in parallel, and the key here is to process the degree reduction signals in parallel. So having these challenges, let's look at the existing parallel algorithms for K-core decomposition. As we explained before, the K-core decomposition process is essentially an iterative peeling process. There are mainly 2 types of peeling strategies aiming to solve the second challenge we just mentioned. They are proposed in 3 papers respectively. Let's look at the offline peeling strategies first. As we said before, the key is to process these degree decremental signals in parallel. The offline peeling uses a parallel histogram to group and count the signals based on their decremental destination. So in this way, the steps are gather the signals, then parallel histogram for counting the signals for different vertices, finally decrease the values of the neighbors' degrees. The online one is even more simple. Instead of counting the signals, online strategy just processes the signals directly using fetch and add operation, which is an atomic operation for changing one single variable's value by a certain value in parallel. It is a constant work operation. So we can summarize the online peeling as decrease the degrees of the neighbors directly using atomic operations. Now we have the different peeling strategies. What are the pros and cons of them? We previously illustrated the concepts of sub-round and round. Actually, there are usually many sub-rounds within a round for most graphs. We find that for offline peeling, there seems no way to reduce the number of sub-rounds because it needs synchronization after the parallel histogram. It will cause bad performance on these large diameter graphs. For example, here is the grid graph with size n by n. It requires n over 2 peeling sub-rounds, while it actually just a 2 core, so we can finish it in a single round, right? Each sub-round means that we need another sub-round of synchronization, which will cause large overhead. So you may be curious, can online peeling avoid sub-rounds? How does it work? Online peeling processes the signals using atomic operations, right? Existing online algorithms design a buffer structure on each thread. When the vertices are removed, they are firstly put into the buffers, and the thread who decreases the degree value of the neighbor under K will add the vertex to the buffer directly and will be processed in the buffer by this thread instead of waiting for next sub-round. In this case, all the peeling sub-rounds will be reduced. So we may ask, is there any issues for the online peeling strategies with buffers? In fact, the buffers they design are opened based on the threads and does not set a proper size of them. So they may be full while processing or empty until the end of this round. So this will cause load imbalance or buffer overflow. Another problem is the contention problem. The signals are processed using atomic fetch and add. What if there are millions of signals taken in parallel? There will be heavy contention problem, which is a huge overhead for dense graphs. So above are the pros and cons of the existing peeling strategies, which aims to solve the peeling challenge. Another thing is about the framework level challenge previously mentioned. How can we keep the vertices in order? The existing works use two structures. Offline algorithm Julian tries to parallelize the sequential bin sort array to achieve work efficiency, so it uses multi-buckets for maintaining the vertices in order. The online algorithm Parquet and PKC use single frontier instead. The main difference here is about the scan times in total. If there is only one frontier, we need to insert the vertices with next degree value into it every round. If there are more buckets, we can insert less, which hides some of the overhead. So as a summary, overall, there are two types of peeling strategies so far. Both of them have their own strengths, but that also means there are some types of graphs they are hard to handle. Specifically, offline peeling cannot avoid massive sub-rounds, so has suboptimal performance on large diameter graphs. In contrast, existing online peeling algorithms can hide the sub-round but faces contention and load imbalance, which makes the performance bad on dense graphs. So we may ask, can we get good performance on these all kinds of graphs? The previous work seemed to focus on different challenges, which is kind of messy. The offline one aims to maintain the vertices better to achieve work efficiency, and the online algorithm reduces sub-rounds for better performance on large diameter graphs. What kind of algorithm do we want? First of all, we want a framework that is work efficient. It shouldn't be hard. Also, it should be practical instead of only keeping the work efficiency in theory, like the bucketing structure in Julian. We will show in the following part that our proposed framework achieves these goals. First, let's see whether the work efficiency is hard to achieve and only exists in theory. Surprisingly, we found that only a small change can make the entire framework work efficient. We don't need multi-buckets, we don't need to care about the pinning strategy. What we need is just to pack all the vertices in the remaining graph. The work efficiency proof of this algorithm can be found in our full paper. The small change of our framework can be adapted to both strategies and make them work efficient. At the same time, it is easy to implement. Then let's review the two strategies in our framework again. For the offline one, because it uses histogram to avoid heavy contention, the problem is that it can't avoid any subrun. And actually, the subrun problem is inherent and severe for offline pinning algorithms. We discard the offline pinning and focus on the online pinning strategy, which is open to many other optimizations. Again, there are two issues: heavy contention and load imbalance problem. For the two problems, we designed two algorithm techniques to overcome them. The first one is a carefully designed two-parameter sampling process for reducing contention. The second one is a vertical granularity control specifically designed for the pinning process to eliminate the subrun overhead and keep a good load balance at the same time. Let's jump into the first challenge: reduce the contention. A quick recap. Since most of the graphs that need K-core decomposition are dense social networks, many atomic operations may happen to a single vertex at the same time, and contention may be heavy. And the experimental results also indicate this critical issue in previous works. Sampling is a commonly used technique for solving contention in parallel algorithms. However, for the K-core decomposition problem, it is not naive to design an efficient sampling process. We will show the overall design of our sampling method and how we make it correct. The initial idea is not complicated and is widely used in other works. While we are doing atomic fetch and add operation for all the red vertices here, we avoid apply all the signals at the same time. We randomly accept partial decremental signals for the degree of the vertex and take actions for the successful random sampling signals. This is easy to understand. So what is the difficulty of sampling in K-core decomposition? As we know, the round ID k keeps increasing, and the degrees of all the vertices may drop below k of this process. If it is still in a sampling mode, there is an error. And a more serious problem is that there are many vertices whose degree are dropping. Sampling is actually a Bernoulli trail with a certain probability to take actions, but we are using the results to estimate the number of trials. How can we promise a correct output? Since we need to scan the alive vertices in each round, we check the sampling counters at the same time. And once the sampling hits ratio is above a certain value, we stop sampling and count its actual induced degree. To achieve a better estimation for high probability concern, we compute the error probability in each round based on the successful sample hits. We prove the correctness of this sampling scheme by a union bound. It's bounded by this term regarding number of vertices, which is with high probability bound. Also, notice that we can detect any error if the sampling is wrong. If so, we restart the algorithm and do sampling in different parameter settings. Due to the time limit, I will omit the math details here. So we see our sampling is good in theory. Does it perform well in practice? Here are some detailed experimental results for sampling. The blue bars are our plain algorithm based on our own algorithm framework, and the red bars are with sampling. Lower is better. On the 8 dense social networks and web graphs, sampling can provide up to 5 times speed up on these graphs. So in conclusion, we improved the contention problem a lot using sampling. Then the next challenge is to reduce the number of subrun and keep a good load balance at the same time. Previously, online pinning works use an unbounded buffer that assumes all the vertices will be added to the buffer, which causes load imbalance and overflow. So in our work, instead of opening large size buffers on each thread, we use a technique called vertical granularity control. We open a local queue for each vertex in each pinning round. The sizes of the queues are fixed as constants. The vertices in the frontier will be added to the head of the queue at the beginning. Then the neighbors to be peeled will be added to the queue by the specific vertex. We open a local queue, right? So each queue will only absorb a range of neighbors. Once the queues are full, the local search will stop, and the remaining vertices will be processed in another subrun. In this case, we sacrifice part of the subrun's reduction because the queue sizes are fixed, but we achieve a better load balance and also avoid potential overflow. The VGC is a better design based on priority queues, and it is of independence interest, which can be adapted to many other algorithms. Let's see how it performs in reality. Although we sacrifice part of the subrun searching depth, the subrun reduction ratios in practice are still good. We can see the results in this figure. The y-axis are subrun numbers for the plain version of our algorithm, and the x-axis is subrun number with VGC. The VGC can provide up to 51 less subrun numbers for large diameter graphs. The acceleration VGC can provide is also more significant. We compared the speedup of the VGC version with our plain algorithm. The yellow bars are plain ones without VGC, and the green bars are with VGC added. Higher is better. We can see VGC can provide a significant speedup for large diameter graphs. Recall that on these graphs, existing offline algorithms perform very poor, and existing online algorithms may face load imbalance problems. Okay, these are the two perspectives of optimizations for solving the problems for dense graphs and large diameter graphs. There seems to be still some overhead remaining in practice, especially the maintenance of the vertices in our framework is still a single frontier. Is there something we can improve for the data structure? Let's look at the overhead regarding the buckets again. If the number of buckets is large, we can reduce scan operations, but the space usage will be large, and the vertex movements overhead will increase. If it is small, increasing rounds of scan operations leads to a larger overhead. So can we design a better bucketing methodology that can balance and further optimize all these issues? Instead of fixing this number, we propose the hierarchical bucketing structure that can achieve this goal. HBS follows a prefix doubling manner. That is, instead of assigning vertices to a certain corresponding degree value, each bucket stores vertices in range of length 1, 1, 2, 4, etc. And the vertices movement destination between them can be done in constant time by bitwise computing. In this way, the movement overhead will be in a good balance. Theoretically, we show the HBS will have the best work for handling the vertices compared to the fixed number bucketing structure. With average movement cost is order of log of max degree, we can see it's better than the other two maintenance methods. We can also check the performance of HBS in the experimental results. The bars are relevant running time for different bucketing number over HBS. HBS here is scaled to 1. For these graphs from different categories with different peeling rounds, HBS can match the best performance of other two or outperform them. Above are 3 techniques we used to get a strong algorithm with detailed experimental results. For the setup, we run all the experiments on a 96-core machine. We test all the baselines and our proposed algorithm on 26 graphs, including different types of real-world graphs and synthetic graphs for extreme cases. Here is the full performance figure of our algorithm with HBS structure for the maintenance and 2 optimizations for online peeling, including sampling and vertical granularity control. We can find for different types of graphs, our algorithm achieves different speedup compared to the baselines. For example, sampling makes performance much better on dense graphs. And VGC is obviously essential, especially for large diameter graphs. HBS provides overall structural improvements on all graphs. So here comes our overall conclusion through the research work. We propose a practical and simple framework for K-core decomposition that achieves work efficiency for different existing peeling strategies. It can adapt both online and offline peeling strategies. And based on the online peeling, we finally optimize our algorithm to gain good performance on all types of graphs. We design parameter sampling and vertical granularity control to solve the problems of existing online peeling algorithms, which have suboptimal performance on different graphs. Besides, we further improve our algorithm by a hierarchical bucketing structure, which balances and hides some of the overhead from different technique designs. This is all my talk. Thanks for everyone's listening. The code is available on GitHub, and feel free to reach out via email if you have any questions.